The National Electrical Code, or NEC, generally applies to electrical installations on the consumer side of the utility's service equipment. In this instance, the utility feeder is considered to be on the utility side, and therefore the NEC does not directly apply to the feeder's conductors. However, the NEC may apply when the utility makes a tap from its feeder to a junction box that is considered to be a consumer-accessible point of connection. This would be the case if the junction box is located on the consumer's property or in a location that is readily accessible to consumers. For taps made at a consumer-accessible point of connection, the NEC requires that the tap conductors be sized in accordance with Article 240. Since connection is being made to a 600 amp distribution panel, the tap conductors must be sized for at least 600 amps. Parallel 350 copper conductors are capable of carrying 600 amps as per Table 310.16 of the NEC. Therefore, parallel 350 copper conductors can be used for the tap to the 600 amp panel. As the utility may have their own requirements for tap conductors, it is important to consult with the utility to determine if they have any specific requirements for the size or type of tap conductors that can be used. To ensure compliance with both NEC requirements and utility requirements, it is recommended to firstly consult with the utility to determine their requirements for tap conductors. Secondly, size the tap conductors in accordance with the NEC and the utility's requirements, whichever is more stringent. And thirdly, use parallel 350 copper conductors if they meet the NEC and utility requirements. Let's delve deeper into these NEC considerations. Article 240 focuses on overcurrent protection, and it is important to ensure that the tap conductors are properly protected against overcurrents. The overcurrent protection device, such as a circuit breaker or fuse, should be sized to protect the tap conductors based on their ampacity. The ampacity of a conductor is the maximum current, in amps, that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. Table 310.16 provides ampacity values for various conductor types and sizes. When using parallel conductors, each conductor must be sized to carry its proportionate share of the total current. In this case, since two 350 copper conductors are being used in parallel, each conductor must be capable of carrying at least 300 amps to achieve the required 600 amp capacity. Additionally, the conductors must be installed in the same raceway or cable, and they must have the same electrical characteristics. This includes the same length, conductor material, insulation type, and termination method. The termination points must also be designed for use with multiple conductors. It is vital to verify that the terminals in the junction box and the distribution panel are rated and listed for the number and size of conductors being terminated. Another important aspect to consider is the tap rule. The tap rule allows for the use of smaller conductors for tap under certain conditions. However, the tap rule has specific requirements regarding the length of the tap conductors and the overcurrent protection. It is essential to carefully review the tap rule to ensure that the installation meets all of the requirements. The length of the tap conductors is a critical factor. The NEC specifies maximum lengths for tap conductors based on the size of the tap conductors and the rating of the overcurrent protection device. These length limitations are designed to prevent the tap conductors from being subjected to excessive overcurrents. In addition to the NEC requirements, the utility may have its own specific requirements for tap conductors. These requirements may include restrictions on the size or type of conductors that can be used, as well as requirements for grounding and bonding. It is crucial to contact the utility and obtain their specific requirements before starting the installation. Grounding and bonding are essential for ensuring electrical safety. The grounding system provides a path for fault current to flow back to the source, which helps to trip the overcurrent protection device and prevent electrical shock. The bonding system connects all of the metallic parts of the electrical system together, which helps to equalize the voltage potential and prevent stray voltages. The NEC has specific requirements for grounding and bonding, and it is important to follow these requirements carefully. The grounding electrode system must be properly installed and connected to the service equipment. The bonding jumpers must be sized appropriately and connected to all of the metallic parts of the electrical system. Furthermore, surge protection may be a valuable addition to the electrical system. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning or other events. SPD are typically installed at the service entrance and at downstream panels to provide comprehensive surge protection. The selection of the appropriate SPD depends on the voltage and current rating of the electrical system, as well as the expected surge levels. When working with electrical systems, safety is paramount. Always to energize the electrical system before working on it. Use appropriate personal protective equipment, such as insulated gloves and safety glasses. Follow all applicable safety procedures and regulations. If you are not qualified to perform electrical work, hire a licensed electrician. Working with electricity can be dangerous, and it is important to take all necessary precautions to prevent accidents. Proper planning and execution are crucial for successful electrical installation. Before starting the installation, develop a detailed plan that includes the conductor sizes, overcurrent protection, grounding and bonding, and surge protection. Obtain all necessary permits and inspections. Follow the plan carefully and ensure that all work is performed in accordance with the NEC and the utilities requirements. Documentation is also important. Keep a record of all work performed, including the conductor sizes, overcurrent protection, grounding and bonding, and surge protection. This documentation can be helpful for future maintenance and troubleshooting. Regularly inspect the electrical system to identify any potential problems. Look for loose connections, damaged conductors, and other signs of wear and tear. Address any problems promptly to prevent them from escalating into more serious issues. By following these guidelines, you can ensure that the electrical installation is safe, reliable, and compliant with all applicable codes and regulations. Understanding the NEC and the utilities requirements is essential for anyone working with electrical systems. Remember to consult with qualified professionals and to prioritize safety in all electrical work. Moreover, consider the long-term maintenance of the electrical system. Regular inspections and maintenance can help to prevent problems and extend the life of the equipment. Develop a maintenance schedule and stick to it. This may include tasks such as tightening connections, inspecting conductors, and testing overcurrent protection devices. Proper maintenance can save money in the long run by preventing costly repairs and downtime. Also, keep abreast of changes to the NEC and other applicable codes and regulations. The electrical industry is constantly evolving, and it is important to stay up to date on the latest requirements. Attend training courses and seminars to learn about new technologies and best practices. Consider energy efficiency when designing and installing electrical systems. Use energy-efficient lighting, appliances, and equipment. This can help to reduce energy consumption and save money on utility bills. The NEC includes provisions for energy efficiency, and it is important to comply with these requirements. Finally, remember that electrical work is a serious undertaking. Always prioritize safety and follow all applicable codes and regulations. If you are not qualified to perform electrical work, hire a licensed electrician. Working with electricity can be dangerous, and it is important to take all necessary precautions to prevent accidents. In addition to the points already mentioned, consider the following aspects of the electrical installation. Firstly, voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can also reduce the efficiency of the electrical system. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. Use appropriately sized conductors to minimize voltage drop. Secondly, harmonic distortion. Harmonic distortion is the presence of harmonic currents in an electrical system. Harmonics can be caused by nonlinear loads such as electronic devices and variable frequency drives. Harmonic distortion can cause equipment to overheat and can also interfere with the operation of other electrical equipment. Use harmonic filters to reduce harmonic distortion. Thirdly, power quality. Power quality is a measure of the characteristics of the electrical power supply. Poor power quality can cause equipment to malfunction and can also reduce the efficiency of the electrical system. Use power quality monitoring equipment to identify and address power quality problems. Fourthly, coordination of overcurrent protection. Coordination of overcurrent protection is the process of selecting and setting overcurrent protection devices so that they operate in a coordinated manner. This helps to prevent nuisance tripping and ensures that the correct overcurrent protection device trips in the event of a fault. Perform a coordination study to ensure that the overcurrent protection devices are properly coordinated. Fifthly, arc flash hazard analysis. An arc flash is a dangerous electrical explosion that can occur when there is a fault in an electrical system. An arc flash can cause serious burns and other injuries. Perform an arc flash hazard analysis to determine the potential arc flash hazards and to implement appropriate safety measures. Sixthly, labeling. Label all electrical equipment with appropriate warnings and instructions. This helps to ensure that workers and others are aware of the potential hazards and how to operate the equipment safely. The NEC has specific requirements for labeling electrical equipment. Seventhly, documentation. Maintain accurate and up-to-date documentation of the electrical system. This documentation should include drawings, specifications, and maintenance records. This documentation can be helpful for future maintenance and troubleshooting. Eighthly, training. Provide training to workers on the safe operation and maintenance of the electrical system. This training should cover topics such as electrical safety, arc flash hazards, and lockout-tagout procedures. Ninthly, emergency procedures. Develop emergency procedures for responding to electrical accidents. These procedures should include steps for de-energizing the electrical system, providing first aid, and contacting emergency services. Tenthly, inspections. Conduct regular inspections of the electrical system to identify any potential problems. These inspections should be performed by qualified personnel. Also, consider the impact of the electrical installation on the environment. Use sustainable materials and practices whenever possible. This can help to reduce the environmental footprint and create a more sustainable electrical system. In summary, the NEC provides a comprehensive set of requirements for electrical installations. It is important to understand and comply with these requirements to ensure the safety and reliability of the electrical system. Consult with qualified professionals and prioritize safety in all electrical work. Remember to consider the long-term maintenance of the electrical system and to use sustainable materials and practices whenever possible. By following these guidelines, one can create a safe, reliable, and sustainable electrical system.